Hello, I'm 85-year-old retired person. I have been worked as space scientist. I'm going to share with you the story of what will happen when the sun dies. Hope you enjoy this documentary. If you found this useful, don't forget to subscribe. Let's dive into, for more than 4.5 billion years, the sun has risen without question. Every morning it climbs into the sky, steady and reliable, bathing Earth in warmth and light. It feels eternal. But the universe is not built on permanence. Even stars are born, they age, and eventually they die. The sun, our life-giving star, is no exception. To visualize the death of the sun, we must first understand its life. The sun is not a fireball, nor a burning object like coal or wood. It is a colossal nuclear engine. At its core, temperatures reach nearly 15 million degrees Celsius. Under unimaginable pressure, hydrogen atoms fuse together, forming helium. In this process, a tiny amount of mass is converted into energy, released as light and heat according to Einstein's famous equation, E equals mc squared. Every second, the sun converts about 4 million tons of matter into pure energy. This fusion process has kept the sun stable for billions of years. Gravity pulls the sun inward, try to collapse it, while nuclear fusion pushes outward, trying to make it expand. For now, these two forces are in perfect balance. This balance is why the sun shines calmly rather than exploding violently. It is also why life exists on Earth. But hydrogen, the sun's primary fuel, is not infinite. Right now, the sun is middle-aged. Roughly 4.6 billion years old, it has already burned through about half of the hydrogen in its core. The remaining fuel will last another 5 billion years. That might sound like an eternity from a human perspective, but in cosmic terms, it is simply the next act of an inevitable story. As time passes, subtle changes are already occurring. The sun today is about 30% brighter than it was when Earth first formed. This gradual increase in brightness happens because helium ash builds up in the core, making fusion less efficient. To compensate, the core contracts slightly, heating up and increasing the rate of fusion. The result is a brighter, hotter sun. This slow brightening will have catastrophic consequences long before the sun actually dies. In about 1 billion years, Earth's oceans will begin to evaporate. The increased solar radiation will accelerate the carbon cycle, stripping carbon dioxide from the atmosphere. Plants will struggle to survive. Oxygen levels will fall. Complex life will disappear. Earth will slowly return to a barren world, not because the sun has died, but because it is growing stronger. By 2 to 3 billion years from now, even microbial life may no longer survive on the surface. The planet will resemble Venus, a scorched, dry world wrapped in thick clouds. Yet the sun itself will still appear peaceful in the sky, shining with deceptive calm. But deep inside, the sun is approaching a crisis. As hydrogen in the core becomes scarce, fusion there will eventually slow down. When that happens, gravity will begin to win. The core will start to collapse under its own weight. As it contracts, it will heat up dramatically. Meanwhile, hydrogen fusion will ignite in a shell surrounding the core rather than inside it. This change marks the beginning of the sun's transformation into something far more dangerous and dramatic. The sun will begin to swell. Over hundreds of millions of years, the sun's outer layers will expand outward. The surface will cool, changing its color from yellow-white to deep orange and red. The sun will become a red giant, an enormous, bloated star hundreds of times larger than it is today. From Earth's perspective, if Earth still exists, the sun will fill a massive portion of sky. Day and night will lose their meaning. The sun's diameter will extend far beyond the current orbit of Mercury, possibly Venus, and maybe even Earth itself. Mercury will be the first casualty. As the sun expands, Mercury will be swallowed entirely, vaporized within the sun's outer atmosphere. Venus will follow, its thick clouds stripped away, its surface melted and erased. Whether Earth survives this phase remains one of astronomy's great questions. Some models suggest Earth will be consumed. Others suggest it may barely escape, pushed outward by solar mass loss. Either way, Earth will be unrecognizable, its surface molten, its atmosphere gone. The sun at this stage will be unstable. Massive solar winds will blow away huge amounts of material into space. These winds will carry the sun's outer layers outward, forming vast, glowing shells of gas that expand into the surrounding darkness. Yet, paradoxically, while the sun grows enormous on the outside, its core continues to collapse inward. Eventually, the core temperature will rise to over 100 million degrees Celsius. At this point, a new kind of fusion will ignite: helium fusion. Helium atoms will slam together to form carbon and oxygen. This moment is called the helium flash, a sudden, violent burst of energy deep within the sun's core. From the outside, the sun may not appear to explode, but internally it is a turning point, the beginning of the end. Helium fusion will stabilize the sun once more, but only briefly. Unlike hydrogen, helium burns fast. The sun will spend only a few 100 million years in this phase, a blink of an eye compared to its long hydrogen-burning life. When helium runs out, the sun will face a final limit. Unlike massive stars, the sun does not have enough mass to fuse heavier elements like iron. When helium fusion ends, there will be no new fuel to ignite. Gravity will once again take control. The core will collapse until it becomes incredibly dense, about the size of Earth, yet containing nearly half the sun's mass. This collapsed core is called a white dwarf. Around it, the sun's outer layers will drift away entirely, forming a breathtaking cosmic structure known as a planetary nebula. Despite the misleading name, it has nothing to do with planets. These glowing clouds will shine in vivid colors: blues from oxygen, reds from hydrogen, greens from ionized gases, illuminated by the dying light of the white dwarf at the center. For a brief cosmic moment, the death of the sun will be beautiful. The planetary nebula will expand outward for tens of thousands of years before fading into the interstellar medium. The sun's material, once part of Earth, oceans, air, and life, will mix with the gas between stars. One day, it may help form new stars, new planets, and perhaps new life. What remains at the center will be the white dwarf, a silent, glowing ember. No longer producing energy through fusion, the white dwarf will slowly cool over trillions of years, fading from white to yellow, to red, and eventually to black. A black dwarf, the theoretical final state, has never been observed because the universe is not yet old enough for one to exist. The sun's death will not be explosive like a supernova. There will be no blinding flash visible across the galaxy. Instead, it will be a slow, majestic fading, a long goodbye written in expanding light and cooling silence. And yet, everything that made us possible will survive in another form. The atoms forged in the sun's core, the elements that warmed Earth and powered life, will not vanish. They will drift through space, becoming part of new worlds, new suns, and new stories written across the universe. The death of the sun is not just an ending. It is a transformation. Long before the sun physically touches Earth, the planet begins to die in silence. The first signs are not dramatic explosions or sudden darkness. They are subtle, almost invisible changes in energy. The sun's brightness increases gradually, but relentlessly. Each century brings slightly more heat than the one before. Glaciers retreat. Polar ice thins. Ocean temperatures rise. Weather patterns become chaotic. Life adapts until adaptation is no longer enough. As solar radiation intensifies, Earth's atmosphere begins to change. Carbon dioxide, the gas that helps regulate temperature, is slowly pulled out of the air through accelerated weathering of rocks. Without enough carbon dioxide, plants struggle to perform photosynthesis. Forests thin, crops fail, oxygen levels begin to drop. The complex ecosystems that took hundreds of millions of years to evolve start collapsing one by one. The oceans, once Earth's greatest stabilizers, turn against the planet. Higher temperatures increase evaporation. Water vapor, a powerful greenhouse gas, traps even more heat. The process feeds itself in a runaway loop. The sky fills with thick clouds. Rain becomes extreme, then rare. Eventually, the oceans begin to boil, not explosively, but persistently, molecule by molecule escaping into the sky. Within 1 billion years, Earth becomes a humid furnace. Surface temperatures rise beyond what any known life can tolerate. The last animals vanish. The last plants wither. The biosphere collapses into extinction. But the planet itself continues to orbit, silent and scorched. As the sun enters the red giant phase, everything accelerates. The sun's radius expands rapidly, and its surface cools, turning a deep red-orange. Though cooler on the surface, the sheer size of the sun means Earth receives vastly more total energy than ever before. The sun begins to dominate the sky. From Earth's surface, if anything could still observe, the sun would no longer appear as a disk, but as an enormous glowing wall stretching across the horizon. The concept of day and night disappears. The sky glows constantly, bathed in red light. Shadows vanish. The stars fade, drown in solar brilliance. Earth's atmosphere is stripped away. Intense solar winds blast outward from the swollen sun. Without a strong magnetic field to protect it, the core long since cooled. Earth cannot hold onto its remaining gases. Hydrogen escapes first, then oxygen, then heavier elements. The sky thins until it is nearly vacuum. With no atmosphere, there is no pressure to keep water liquid. Any remaining oceans vanish into space. The surface cracks under extreme heat. Rocks soften. Mountains slump. The crust begins to glow faintly red, like metal in a forge. Earth becomes a molten world. The planet's rotation may slow as tidal interactions with the sun intensify. One side may face the sun continuously, locked in an eternal blaze, while the other remains only slightly less hostile. The surface reshapes itself under gravity and heat, erasing all traces of continents, oceans, and civilizations that once existed. Then comes the moment of closest approach. As the sun continues to expand, Earth's orbit changes. The sun loses mass through powerful stellar winds, which can cause surviving planets to drift outward. But drag from the sun's extended atmosphere may pull Earth inward at the same time. It becomes a delicate cosmic tug-of-war. If Earth is pulled inward, it will cross a fatal boundary. The planet enters the sun's outer envelope. Temperatures soar to thousands of degrees. The crust vaporizes instantly. The mantle follows. Earth is torn apart atom by atom, absorbed into the sun's gaseous layers. What once was a living world becomes fuel, briefly lighting the sun's dying glow. If Earth escapes engulfment, its fate is only slightly less final. The sun eventually sheds its outer layers entirely, leaving behind a glowing planetary nebula. Earth, stripped and sterilized, continues orbiting the sun's exposed core, the white dwarf. The sky turns black. The nebula glows faintly, expanding and fading over tens of thousands of years. Earth is now a dead relic. Its surface is frozen on the outside and scorched within. There is no air to breathe, no water to flow, no sound to carry. The sun, once a blazing presence, is now a small, brilliant point of light, no larger than a star in the night sky, yet far brighter. Over billions of years, even that light fades. The white dwarf cools slowly, radiating away its remaining heat. Earth's orbit stabilizes in eternal darkness. The planet becomes a cosmic fossil, one of countless dead worlds drifting through a quiet galaxy. Nothing remains to tell the story of oceans, forests, or minds that once gazed upward and wondered about the stars. Except the atoms themselves. Iron from Earth's core. Oxygen from ancient seas. Carbon from once living cells. All of it may one day be scattered by gravitational interactions, collisions, or passing stars. Some of it may become part of new planets. Some may fall into new suns. Some may form the chemistry of future life. In that way, Earth does not truly disappear. It transforms. The death of the sun erases our world, but not our legacy in the universe. And as devastating as this vision is, it is not unique. Across the galaxy, countless planets are meeting the same fate right now. Suns are swelling, worlds are burning, nebulae are forming. The universe is in constant motion, endlessly creating and destroying without pause or preference. The death of the sun is not a tragedy written only for Earth. It is a chapter in a cosmic pattern. In the vastness of the universe, stars die in many different ways. Some fade gently, like dying embers. Others explode with such violence that they outshine entire galaxies for a brief moment. The way a star dies depends on one simple factor: mass. The sun is an average star. Not small, not massive, not extreme. This average nature is the reason its death will be slow and relatively peaceful. But most stars in the universe are not like the sun. Many are far larger, far more energetic, and far more dangerous when they reach the end of their lives. To understand the uniqueness of the sun's death, we must look at how other stars die. Massive stars, those 8 or more times heavier than the sun, live fast and die violently. Their cores burn through hydrogen at an astonishing rate. While the sun will live for roughly 10 billion years, some massive stars exhaust their fuel in just a few million years. These stars burn bright, blue, and unstable, pushing against gravity with immense nuclear pressure. Inside these massive stars, fusion does not stop at helium. They fuse carbon, oxygen, neon, silicon, building heavier and heavier elements in layered shells, like the layers of an onion. Each fusion stage releases less energy than the one before. Eventually, the core becomes iron. Iron is the final dead end of nuclear fusion. Fusing iron does not release energy, it consumes it. When an iron core forms, the star has nothing left to support itself. Gravity wins instantly. The core collapses in a fraction of a second, triggering one of the most violent events in the universe, a supernova. In a supernova, the star's core collapses to extreme density, then rebounds outward with unimaginable force. A shockwave tears through the star, ripping it apart. The explosion releases more energy in seconds than the sun will emit over its entire lifetime. For a brief moment, a single star can outshine every other star in its galaxy combined. The elements forged in this explosion, gold, uranium, iodine, many of the atoms in your body, are blasted into space at thousands of kilometers per second. Supernovae are the reason the universe contains complex chemistry. Without them, planets like Earth would never exist. But supernovae leave behind corpses. If the collapsed core is massive enough, it becomes a neutron star, a city-sized object with the mass of the sun compressed into a sphere just 20 kilometers across. Neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses. Some rotate hundreds of times per second, their magnetic fields trillions of times stronger than Earth's. If the core is even more massive, gravity continues its collapse beyond all known limits, forming a black hole, a region of space where space-time itself is torn open, and not even light can escape. Compared to this violence, the sun's death seems almost gentle. The sun will never fuse iron. It will never collapse catastrophically. It will never explode. Instead, it will shed its outer layers slowly, forming a planetary nebula, and leave behind a white dwarf. A white dwarf is a strange object. It contains about half the sun's mass compressed into a sphere roughly the size of Earth. A teaspoon of white dwarf matter would weigh several tons. The pressure inside is supported not by fusion, but by quantum mechanics, specifically electron degeneracy pressure, a fundamental limit imposed by the laws of physics. White dwarfs do not burn. They glow. They shine with residual heat, slowly cooling over trillions of years. They are cosmic tombstones, marking where stars once lived. Yet even white dwarfs can meet dramatic ends under certain conditions. If a white dwarf is part of a binary system and steals matter from a companion star, it can grow too massive. When it exceeds a critical limit known as the Chandrasekhar limit, it collapses and detonates in a type Ia supernova, an explosion so uniform that astronomers use it to measure the expansion of the universe. Our sun is safe from this fate. It is alone, isolated, destined to fade quietly rather than explode. This makes the sun's death not only gentle, but rare in its simplicity. Across the galaxy, supernovae reshape star systems, sterilize nearby planets, and trigger new waves of star formation. Black holes warp space and time, consuming matter and bending light. Neutron stars unleash gamma-ray bursts capable of destroying life across thousands of light years. The sun will do none of these things. Its death will not threaten distant civilizations. It will not rewrite the structure of the galaxy. It will simply return its material to space, softly, without violence. This quiet ending is the reason life had time to evolve on Earth. Violent stars die too fast. Their chaotic environments make stable planetary systems unlikely. The sun's long, stable life allowed billions of years of calm, enough time for chemistry to become biology, and biology to become consciousness. In this sense, the sun's death is the final act of a long act of generosity. It gives life everything it needs, then steps away without destruction. But this raises a profound question. If the sun's death is inevitable, could intelligence survive it? Could a civilization foresee this fate and escape it? Could humanity, or any species, outlive its star? The death of the sun is inevitable, but extinction is not necessarily guaranteed. Unlike asteroids, supernovae, or sudden cosmic catastrophes, the sun's demise unfolds over billions of years. It is not a surprise. It is not sudden. It is written clearly into the physics of stars. This long timescale changes everything. It means that any intelligent civilization orbiting the sun, human or otherwise, would have immense time to prepare. The real question is not whether the sun will die. The question is whether intelligence can outgrow its birthplace. Long before the sun becomes a red giant, Earth will already be uninhabitable. But this does not mean humanity must vanish with it. The future of survival begins with leaving the surface of Earth and learning to live beyond a single planet. The first step is space. In the coming thousands to millions of years, a technologically advanced civilization could spread throughout the solar system. Mars, icy moons like Europa and Enceladus, and artificial habitats built in space could host vast populations. Orbiting colonies, free from planetary gravity, could be positioned at optimal distances from the sun, adjusting their orbits as solar output changes. As the sun grows brighter, habitats could slowly migrate outward. This is not science fiction. It is orbital mechanics. By gradually increasing orbital energy, entire populations could drift farther from the sun, staying within a comfortable temperature zone. With enough energy and control, even planets could be moved. The idea of planetary migration, once considered fantasy, has been studied seriously in astrophysics. Using repeated gravitational interactions with asteroids or controlled propulsion over millions of years, Earth itself could theoretically be shifted outward. But the red giant phase is far more challenging. As the sun expands, its radiation becomes extreme and unstable. Solar winds intensify. The inner solar system becomes a dangerous environment. At this stage, survival would likely require abandoning the sun entirely. Interstellar migration becomes the next frontier. By the time the sun approaches its red giant phase, humanity, if it still exists, would have billions of years of technological evolution behind it. Chemical rockets would be ancient history. Advanced propulsion methods, such as nuclear fusion, antimatter drives, or even light sail systems powered by stars, could make travel to nearby star systems achievable. The galaxy is vast, but it is not empty. Within a few dozen light years of the sun lie hundreds of stars, many of them smaller, longer-lived red dwarfs. These stars burn slowly, shining for trillions of years. Around them may orbit planets or stable regions where artificial habitats could thrive far longer than Earth ever could. In this future, stars are no longer permanent homes. They are resources. Advanced civilizations might construct megastructures, vast artificial systems designed to capture stellar energy. The most famous concept is the Dyson swarm. Billions of orbiting collectors harvesting energy directly from stars. Such systems could power civilizations at scales beyond current imagination, allowing them to exist independently of planets. When a star like the Sun begins to die, its energy output changes, but it does not vanish immediately. A civilization capable of stellar engineering could adapt its infrastructure to these changes, maintaining energy supply long after Earth is gone. Even the white dwarf remnant of the Sun could be used. White dwarfs emit steady heat for trillions of years. Habitats could orbit them closely, drawing energy from their residual warmth. In a universe where stars are aging, even dying suns can still provide power. Some theories go even further. They suggest that intelligence might eventually detach itself from biological form entirely. Minds could exist as digital entities, running on vast computational structures powered by stars or black holes. Time itself could be manipulated, slowed subjectively, allowing consciousness to persist on minimal energy over unimaginable durations. In this future, the death of the sun is not an end. It is a relocation. But survival is not only about technology. It is also about memory. If humanity leaves the solar system, Earth becomes a monument, a silent origin world, forever marking where consciousness first awakened under the light of a yellow star. The story of the sun would become part of cultural memory, mythologized across generations. A star that once rose every morning. A world that once lived. Yet there is another possibility. Humanity may not survive long enough to witness the sun's death. Civilizations are fragile. History shows that intelligence does not guarantee wisdom. Environmental collapse, self-destruction, or unforeseen cosmic events could end our story long before the sun demands it. In that case, the sun will die alone. It will expand, shed its layers, and fade into a white dwarf without witnesses. No eyes will watch the nebula bloom. No minds will understand its beauty. The universe will continue, indifferent and silent. And yet, even in that silence, meaning remains. The atoms that once formed life will drift onward. The energy that once powered thought will disperse. The universe loses nothing. It only rearranges. Whether humanity survives or not, the sun's death reminds us of something profound. Existence is temporary, but not pointless. Life does not need to last forever to matter. As the sun ages, its death does not occur in isolation. The entire solar system feels the change long before the final transformation begins. Planets, moons, comets, and even distant icy objects respond subtly to the sun's shifting gravity and energy output. When the sun loses mass during its red giant phase, gravity weakens. Orbits expand. Worlds drift outward, their paths reshaped by a star slowly letting go of its material. The solar system becomes looser, more fragile, more exposed to the influence of passing stars and galactic tides. The asteroid belt destabilizes. Objects that once followed predictable paths are nudged into new orbits. Some are flung into deep space. Others spiral inward, vaporized by intense solar radiation. The Kuiper Belt, home to icy remnants of planetary formation, begins to scatter. Comets rain inward briefly, creating glowing trails that vanish instantly in the sun's swollen atmosphere. The familiar structure of the solar system dissolves. Jupiter and Saturn, massive enough to survive the red giant phase, become dominant gravitational players. Their moons, some once frozen worlds, may briefly experience warming as the sun expands. For a short cosmic moment, distant moons could host liquid water beneath their surfaces, illuminated by a red sky and a massive dying sunday. But this warmth is temporary. As the sun sheds its outer layers, radiation becomes unstable. Solar winds strip atmospheres from moons and planets alike. Any brief window for life closes rapidly. What remains are barren worlds orbiting a star that no longer behaves like the one they formed under. Then comes the planetary nebula phase. The sun's outer layers expand outward at tens of kilometers per second, forming vast shells of glowing gas. These shells interact with the solar system's remaining bodies, bathing them in ionizing radiation. The nebula's colors, emerald greens, deep reds, electric blues, are not peaceful. They are signatures of atoms being torn apart and energized by intense ultraviolet light. From a distance, this nebula would be beautiful. From within, it is lethal. Eventually, the nebula dissipates. The solar system emerges into darkness around a white dwarf Sunday. The planets that remain orbit a stellar corpse that emits no warmth, no nurturing light, only faint residual heat and harsh radiation. The solar system becomes a graveyard. But the universe does not stand still. Over billions of years, passing stars slowly disrupt these orbits. Some planets are ejected entirely, becoming rogue worlds drifting through interstellar space. Others spiral inward and collide with the white dwarf, releasing brief flashes of energy before vanishing forever. The solar system, once vibrant and ordered, gradually unravels. Even time itself behaves differently in this future. As stars age and galaxies evolve, entropy increases. Energy becomes harder to extract. The universe cools. The era of star formation slows. Fewer new suns ignite. The night sky grows darker with each passing billion years. The sun's death is not just a local event. It is part of the universe's long journey towards stillness. Yet even in this fading cosmos, complexity persists for a time. White dwarfs remain as stable energy sources far longer than main sequence stars. Advanced civilizations, if they exist, may choose to cluster around them, using their steady output to power computation and artificial worlds. In this far future, the sun's white dwarf remnant could become part of a network of ancient stars, quiet anchors in a cooling universe. And then there is the question of memory. How long does a civilization remember its origins? Even if intelligence survives, even if minds migrate between stars, cultural memory erodes. Languages change. Records decay. Digital archive fell. Over millions or billions of years, even the story of Earth and the Sun may become fragmented, mythologized, or lost entirely. A once bright yellow star may become a legend. A blue planet may become a symbol rather than a place. And yet, traces remain. The isotopic signatures in atoms, the arrangement of elements, the faint chemical fingerprints left behind by life itself. Long after minds forget, physics remembers. This is the deepest truth of stellar death. Nothing is truly erased. The sun's photons have already traveled across space, touching distant dust clouds, altering chemistry light years away. The energy it emitted billions of years ago is still moving outward, carrying information about its existence. Even when the sun is gone, its light will continue. Somewhere far beyond the Milky Way, a photon emitted today may still be traveling when the last stars burn out. It will carry no memory of Earth, no story of life, but it will prove that the sun once existed. And that is enough, because the universe does not require witnesses. It unfolds regardless. The death of the sun teaches us humility, not despair. It reminds us that permanence was never promised. What was given instead was opportunity, a window of stability in which complexity could emerge and meaning could be created. That window was wide enough. And for a time, we lived inside it. When the sun finally dies, there will be no audience, no annoncement, no final sonrisa. There will be only physics, unfolding exactly as it has for billions of years across the universe. The planetary nebula that forms from the sun's outer layers will glow briefly against the darkness, a delicate shell of color expanding into space. For a moment, tens of thousands of years, it will be visible from afar, a luminous ghost marking where a star once lived. Then even that will fade, thinning into the interstellar medium until it becomes indistinguishable from the surrounding galaxy. What remains is the white dwarf, small, dense, and silent. It does not burn. It does not shine with purpose. It simply cools, radiating the last heat of a star that once defined an entire solar system. Over trillions of years, it will fade from white to yellow, from yellow to red, and finally toward darkness. Long after galaxies collide and stars are reborn, the sun's remnant will still be there, slowly surrendering energy to the cold of space. But the true legacy of the sun is not what remains. It is what once was. For nearly 10 billion years, the sun existed in balance, holding gravity and fusion in perfect tension. That stability allowed planets to form, oceans to persist, atmospheres to evolve, and chemistry to cross the threshold into life. The sun did not choose this role. It followed the laws of physics. And yet, within those laws, something extraordinary emerged. Consciousness. For a brief moment in cosmic time, matter became aware of itself under the light of a single star. The sun illuminated mountains, seas, forests, and eventually minds capable of asking questions about their own origin. It powered curiosity, memory, and meaning. The sun never knew this, and yet it made it possible. When we speak of the sun's death, we often frame it as a catastrophe. But in the universe, death is not an exception. It is a process. Stars die so that galaxies can evolve. Elements scatter so that complexity can arise. Endings are not failures. They are transitions. The carbon in your body was once inside stars that died long before the sun was born. Those ancient supernovae ended violently, yet their destruction created the raw materials for life on Earth. In the same way, the sun's death will seed the future, quietly, without drama. Its atoms will drift through space, becoming part of new clouds, new stars, and perhaps new planets. Somewhere, far in the future, another world may form using traces of what was once our sun. And on that world, life may arise again, never knowing the story of the star that made it possible. In this sense, the sun is not unique. And yet, to us, it is everything. It is easy to feel small when confronting cosmic timescales. 5 billion years dwarfs human history. Trillions of years make civilizations seem meaningless. But this perspective misses something crucial. The universe does not measure value in duration. A moment of awareness, no matter how brief, changes the universe forever. The fact that the universe produced beings capable of understanding stars means that the universe has, in a way, come to know itself. The sun's death will not erase that achievement. Even if humanity vanishes, the truth remains. Under the light of one ordinary star, matter organized itself into life, and life learned to look back at the cosmos that created it. That fact can never be undone. The death of the sun is not the end of a story. It is the final punctuation mark in a sentence that began with a collapsing cloud of gas billions of years ago. Everything between those moments, oceans, storms, thoughts, dreams, exists because of a stable star burning quietly in a spiral galaxy. And when that star fades, the universe will not mourn, but it will remember, in its own way, through the structures that follow, the stars that ignite, and the worlds that form from recycled light. In the end, the sun teaches us a simple truth. Nothing lasts forever, but everything matters while it exists. And for a brief, luminous moment in cosmic history, the sun was home.